Buenas noches a todos. Continuamos con la segunda jornada del Simposio Internacional en Sustentabilidad en la Construcción de Pavimentos. Esta noche, como primera ponencia, presentamos al doctor Shane Underwood. Es docente en el Departamento de Ingeniería Civil, Ambiental y de Construcción en la Universidad Estatal de Carolina del Norte. Fue asistente docente en la Universidad Estatal de Arizona, en la Facultad de Ingeniería Sustentable y Medio Ambiente Construido. Su investigación se enfoca en el desarrollo mejorado de sistemas de pavimentos a partir de estudios mecánicos experimentales sobre materiales de pavimento y a partir de estudios sobre la vulnerabilidad de dichos sistemas a la incertidumbre climática y tecnológica. Esta noche estará presentando Innovación en Ingeniería y Materiales, parte 3, Uso de materiales reciclados. Welcome, Professor. Please continue.
Muchas gracias. Hola a todos. Primero, disculpado por no hablar bien español. Hoy yo presentaré en inglés. Espero que está bien. Lo siento. Thank you all very much for coming today. I again apologize for not speaking Spanish very well. I hope it's okay that I'll be presenting today in English. Let me start by sharing my slides. So you should now all see the slides. If not, please someone let me know and I will try again. But I hope you can see that today my talk is going to be on using recycled materials. This is something that, at least in our lab and in our state, we do a lot of, and we've gained a lot of experience. So I'm going to talk to you today about research that we have conducted in our lab, and also some basic practices for using recycled materials in the US, which is very highly varied. But I hope that today's talk gives you some useful information, and maybe through our discussions I can clarify where there are any issues. Before I begin, I want to mention that the work that I'm showing today is actually the outcomes from several different resources, including many researchers at North Carolina State University. I want to particularly acknowledge Dr. Cassie Castorena, who is another faculty member here at North Carolina State, who does a lot of research on recycled materials. Her and I work very closely together on a few research projects, and I'm presenting work from that, which includes both of our findings and our research, as well as researchers at the Virginia Transportation Research Center, who are instrumental in this work, and then several graduate students that you see listed on the left-hand column, as well as several industry publications that I'll be citing and referencing throughout today's talk. Now, for the talk today, I'm going to talk through a few different topics. So I want to first start off by introducing this issue of recycled materials, why it's such an important issue in the United States, at least, and I suspect internationally. After I do that introduction, I will talk about recycled materials that we use in the US for asphalt concrete. We particularly recycle existing asphalt pavements into new pavements, but there are other materials that we use as well. And I'll talk about the particulars and peculiarities of using different kinds of recycled materials. And then I want to spend the majority of today's presentation talking about design and performance of the mixtures using recycled materials. So I'll talk about RAP mixture performance, which is reclaimed asphalt pavement. These are mixtures that pavements that use asphalt concrete that incorporate recycled materials. I'll also talk about a framework that we have been developing at North Carolina State and others to think about how these recycled materials contribute to asphalt pavement performance. And so we've developed this sort of, again, in combination with others, a sort of set of three or triad issues that affect how recycled materials contribute to asphalt pavements and ultimately how those pavements perform. And then I'll finish with a discussion of recycling agents and how that can contribute and positively affect recycled materials. I've got about an hour and 20 minutes or so of presentation today, and I'll try to cover these things in an efficient way, but I'll also try to speak a little bit slowly in order to try to make it as clear as possible. So if we start with an introduction, when we look at the US and why we might be interested in recycling materials, it largely comes down to the scale and scope of our pavement transportation network. In the US, the pavement network is the largest civil infrastructure investment that our country has made. It consists of about 3.7 million kilometers of paved roads. Most of those are paved with asphalt, at least at the very top surface layer. If we look at the number of lane kilometers, it's close to 10 million lane kilometers in the US. Each year in this country, by some estimates, we spend about $32 billion in US currency just on the materials that we use in those pavements. That does not constitute the additional 130 billion or so that we spend on the engineering, on the management, on the delivery, and other aspects. So we have a substantial investment in our infrastructure system here in the US, and a large portion of that investment goes into the materials that we use to pave our asphalt or our roads. In the US, we also produce a lot of asphalt concrete. About 382 million tons are produced each year. That works out to be around 1.6 million tons per day if we're looking at normal production days, which is quite a lot of asphalt concrete to produce in a given year. And those productions go to repaving operations or new pavement construction. We have lots of different applications that we use for those asphalt concrete mixes. Given the scale, the size of the pavement network, and the size of how much we spend each year on asphalt concrete, the potential for savings is actually quite large. By one estimate, the National Asphalt Pavement Association has estimated that we save about $7 a ton when we use reclaimed asphalt pavements into those mixes. Now, that doesn't sound like a lot. It's actually a pretty low portion of the total cost of that asphalt mixture. But because we produce so much material in a given year, those savings add up to be about $3.3 billion, or about 10% of what we spend in total each year on materials. Those are not insignificant savings, and that's only from one recycled material, that's reclaimed asphalt pavements. In addition to the economic savings that recycling can afford, we can also observe or have environmental savings. Again, NAPA, our National Asphalt Pavement Association, estimates that we save about 21.2 million tons of CO2 equivalent by using reclaimed asphalt pavements in the US, again, on an annualized basis. Again, these numbers are large because our infrastructure system is so large in the US. Now, we spend a lot of time thinking about asphalt concrete with recycling materials because despite the fact that the US is a single country, there are more than 50 individual transportation agencies that are responsible for the design, the construction, and the management. And each of those agencies carries with them their own individual and independent approaches to dealing with these materials, asphalt concrete in general, but also reclaimed asphalt pavements. And so we spend a lot of time in our country looking at these recycled materials to try and understand how they behave, because there are so many different contexts in which these are used. Now, I've given you some benefits from a an economic perspective and from an environmental perspective. But really, one of the big questions and one of the big themes of my talk today is a question about what is the total net benefit that we achieve when we use recycling materials. There is a clear evidence that we obtain good initial reductions in environmental impacts, reduction in the cost of these materials. But what about things like cracking or rutting? As I'm going to talk about today, there is evidence that sometimes these recycled materials can lead to more cracking, perhaps less rutting, but so that's a trade-off. We might be experiencing some lower costs and lower net initial environmental impacts, but if the pavement is cracking and not lasting as long, then we actually have a net effect from using these recycled materials. And so we want to think about those performance impacts across many different distresses, including, as I said, cracking and rutting, but also skid resistance. Asphalt concrete using reclaimed materials or recycled materials may have systematically different behaviors in terms of macro texture, in terms of friction behaviors, because the effective asphalt contents are different, because the mixes themselves might end up being finer. So we need to be worried about that. And this is growing in importance in the US as we talk about driver safety and pedestrian safety. We also repairable these materials might be. Not in the case of wrap, but there might be some other recycled materials that turn into being challenging to recycle or reuse, and we need to think about that. So while it's clear that there may be some initial benefits, we really need to take a closer look before we jump into using a lot of recycled material to think about what are the potential long-term impacts and benefits from using these recycled materials. And that's going to be a thread and a piece that I want to talk about throughout my presentation today. So with that, let's transition to the next part of the presentation. What materials are commonly recycled into asphalt pavements? Well, we actually recycle a lot of materials into asphalt pavements. I think in the US, but also internationally. I do not know what the Bolivian experience is with recycled materials specifically, but I know that it is widespread nationally to use recycled materials in some form or fashion. Usually owing to the fact that the system is so large that we're able to incorporate recycled materials pretty effectively. The first material I'll talk about are reclaimed asphalt pavements. Reclaimed asphalt pavements, or RAP, are generally used in centralized plant-produced concrete mixtures at rates up to about 50%. Now, the 50% usage rate is considered high RAP in the US. As I'll talk later, the typical dosage rates are much, much lower. I'm talking here also about RAP that is transferred back to a centralized plant and is mixed at that plant. There are also stations of using reclaimed asphalt pavements in place recycling. I'm not going to spend any time on that. It is a prevalent technology here in the US and elsewhere, but I'm going to focus exclusively on centralized plant-based reclaimed asphalt pavement recycling. Now, there are some facts that are important to know about recycling asphalt pavements or reclaimed asphalt pavements. Reclaimed asphalt pavements, or pavements, asphalt concrete pavements in general, are considered to be 100% recyclable. We recycle a lot of asphalt pavements back into mixes here in the US. For the most part, 94% of the time, those materials are recycled back into pavements. So a circular use of these reclaimed materials is an important part of why reclaiming asphalt pavements is so important. Most of the time, those recycling processes are used to bring the reclaimed asphalt pavement back into asphalt concrete. So a truly recycling application. A portion of those 94% recycled rates incorporate using RAP into aggregate bases or using them as shoulder repair, but the vast majority are recycled back in new asphalt concrete pavements to create a circular-based those materials. In 2019, the last year that data was available on these recycled rates, we recycled in our country about 89.2 million tons. And I will emphasize that that number are US tons, not metric tons. So less in terms of metric tons, but nearly 89 million tons of recycled material. We estimate in our country, we actually have a backlog of reclaimed asphalt pavements. About 138 million tons were estimated to exist in stockpiles. Although these are backlogged, they are not stored in landfills, so it's considered to be a net positive benefit for the environment. Contractors are incentivized to retain RAP materials because of the cost savings to them, and also because usually those materials are simply given to them by the state DOT as means to get rid of the waste from new road construction. And you can see how much money this is saving just by stockpiling that material. You'll see on the right-hand side of this graph, or on the graphs on the right side, that the tons of RAP materials have increased over time. So we continue to use more tonnage, at least, of RAP materials. And that's been the case for the last 10 or 15 years. Part of the reason that the tonnage of RAP materials increases has to do with the fact that we have improved some of the engineering capability with these RAP materials. As states gain more experience with them, they're more likely to use RAP. And so we've got a lot of increased experience, and with that comes increased usage rates. The map on this slide is basically meant to show you the typical usage rates in the US. So where I live, North Carolina, our average RAP usage rate is 24%. But this is the average rate. There are surface asphalt mixes that use up to about 40% RAP in some cases. And these have been used successfully. Some of the engineering behaviors are more challenging, but there are experiences that use very high RAP dosages. Also see that not every state is as permissive as North Carolina is. So for example, the state of Arizona here in the western part of the US uses a lot less RAP. This state, at least the southern part of that state, is quite hot, and their concern stems from the embrittlement that may occur when RAP-based materials are utilized. If you average the dosage rates across the US, this comes out to be about 20%, which is used, again, across the US with quite a bit of variation depending on the exact state. But again, that experience is fairly broad, and many agencies have some level of familiarity with using reclaimed asphalt pavements on their roadways. Now, the vast majority of the usage of RAP is directly into asphalt fixtures. However, there are other applications related to pavements that are worth mentioning. The first that I'll mention is in the bottom here, this ABC. This stands for aggregate base course, and it basically is the use or incorporation of reclaimed asphalt pavements into the aggregate bases. Now, this has some benefit because usually RAP materials are very fine graded, which means that they compact very densely, and depending on the time of the year when they're placed, you may get some minor amount of cementing action from the aggregate base. This is generally considered to be positive, but you also can look at the alternative, which is using reclaimed asphalt pavements directly concrete mixtures, which has a higher net benefit. And so there aren't a lot of states that use RAP in aggregate base as a normal operation. And part of that has to do with the value statement of using it as an aggregate versus using it in a more high value layer like the asphalt concrete directly. There are also examples of using wrap materials in chip seals. Chip seals, again, consists of a thin layer of asphalt binders with aggregate spread on top. And there are examples of using graded wrap materials in those chip seals. That has a lot of benefit because as you see on the image on the top, on the right, we have a wrap-based chip seal. It looks dark in color. It looks like a real paved, dense graded road when it's completed. The citizens like that. It also cuts down on the dust that you will get coming off these chip seals. But it does create problems because the chip seal tends to only use the coarse fraction of the wrap. But as you can see in the aggregate base, there's quite a bit of fine material left over. So when people and agencies use wrap in chip seals, there can be some stockpile management issues that have dealt with and overcome. One way that some agencies have found to deal with that is to incorporate the wrap-based materials into slurry seals or microsurfaces, which do use the fine fraction. And so it's kind of a balance. You can use the coarse fraction for chip seals and the fine fractions for the micros and slurry seals that you might use. There are a lot of applications of wrap in asphalt, not just in using them in the asphalt concrete itself. So we have a lot of different ways that wrap can get incorporated. A related material with wrap are recycled asphalt shingles. So these are shingles that are either removed from the roofs of someone's home during a roof replacement, or they may be reclaimed from a manufacturer's waste. So when manufacturers create the shingles, they may actually produce quite a bit of waste that can be incorporated and used in asphalt concrete. Technically, RAS are incorporated at up to about 5% dosage, much smaller than wrap, but the asphalt content for a typical shingle is much higher. So a typical reclaimed asphalt shingle might have something between 20 and 30% asphalt binder content. And so use lower amounts of the shingles and get a total net benefit in the binder content. As you can see images on the screen, there are issues that have to be dealt with, especially when we use tear-off or post-consumer waste materials. You can see these gentlemen in the upper corner here are dealing with leaves, backing paper, lots of different components in this waste stream, as you would imagine from a construction site. You can also see this in the image on the left, where you see all of the paper and all of the waste materials that come with roofing replacements. And so those materials have to be separated in order to produce very good, usable, recycled asphalt shingles for use in pavement. You can see at the top what a typical process shingle would look like. It's very, very fine. The challenge with this is making sure that this stays dry because it can absorb quite a bit of water in it. But usually once the materials are sorted, they're ground into a fine powder essentially, and then those get blown back into the asphalt mix at the centralized plant. Another image here just to emphasize that there are two streams of asphalt shingles, the so-called post-consumer waste or post-consumer asphalt shingle is taken directly from people's roofs. This material may have been sitting in service for 10, 15, 20 years. So it's going to be stiff. It's also going to be much more varying in terms of composition and behavior. We can contrast manufacturer waste shingles that would be produced during the manufacturing process and would be a much more consistent stream, so considerably less oxidized or aged So they're a little bit more capable of being used in asphalt pavements. The use of asphalt shingles has declined somewhat in the US in recent years. One of the reasons for the decline in asphalt shingles has to do with the rheology of those materials. So here I'm showing you a photograph from one of our students at NC State who was working with a manufactured waste shingle. So this is actually the softer of the shingles. And this binder can, although it does look like it, is actually heated up to about 150 degrees Celsius. And you can see just how stiff and immovable this material is. That's even more evident on the right. Again, keep in mind, this is binder that is heated to 150 degrees Celsius or more and still behaves as a brittle solid material. So we've got big challenges when it comes to using reclaimed asphalt shingles or recycled asphalt shingles because their rheology is so very stiff. There have been several studies to look at this issue. I'll show you at least one here to kind of give you an idea. For those of you that are familiar with the USPG grading system, there have been various researchers who have tried to PG grade of reclaimed asphalt shingles. And here are just some examples. So a typical high temperature grade for North America would be a PG 64 binder. And you can see these numbers are degrees Celsius. If you're not familiar with the grading system, the fact that these numbers are almost 2/3 or twice as large as a typical grading tells us that they are very stiff, giving PG grades up to, in some cases, 175 degrees Celsius. And this happens to be a post-consumer shingle. So this number would have been out, that shingle would have been in this case, Alabama, which is in the southeast part of the US, for up to 20 years and had aged quite a bit in that time. Now, if you've ever run a test or tried to run tests on asphalt binders that are this stiff, you'll know that there's quite a bit of uncertainty associated with the very fact that it's so very stiff of a material. So these numbers we should treat very cautiously. But what you can see from this is that the numbers are very high, much higher than typical. And they also range across a pretty broad number from 121 up to 175.4. And so incorporating those materials into asphalt pavements, you would expect very different properties for the mixture using this high stiffness, RAS for a relatively lower stiffness RAS from the Minnesota case. This is just one study, probably about another half dozen studies out there that basically conclude the same thing. Recycled asphalt shingles are very stiff. They are slow to rise and may or may not actually even be liquefied at a typical dosage temperature that we would see in an asphalt plant. A second challenge in dealing with RAS has to do with the aggregate particles themselves. Now, the aggregate particles that are used in shingles are not necessarily as angular as the ones that we use in asphalt concrete, but they can also have very different gradations than we typically see in the sand stockpiles that we use to make asphalt concrete pavements. I'm showing you one example of a case of 3 mixes, one having no RAS, okay, this is just the gradation size, one having 4% RAS, and one having 3% RAS. And I want to call your attention to the fact that in this 3% RAS case, we have this hump gradation right around the restricted zone in our gradation band. This hump gradation is a characteristic telltale sign of natural sands that are not compacting, that will not compact well. And in fact, we actually see in this particular mix that the mix behaves very tender. This CO mix was very tender, whereas this other mix that had even more RAS, but from a different source, we don't see that tender behavior, and we don't see that change in band, in that gradation. So we have to be very careful when using recycled asphalt shingles, both in terms of how stiff the asphalt binder is, but also the gradation of the sand particles that are used in that shingle. All of that has to be taken into account and considered. Now, besides reclaimed asphalt pavements and recycled asphalt shingles, which are really important because they have with them asphalt binder, so we can get some potential benefits if we can mobilize the binder effectively. We also use other recycled materials. One of the hot topics in the US in the last, I would say, 3 years or so have been the use of recycled plastics into asphalt concrete. Now, the idea of using recycled plastics is not particularly new. There are examples of using recycled plastics at least as early as the 1970s. Those exist in 4 different countries that I found in our review, and there are probably more that I've missed, but we see usage in Europe and the US. You also will find examples, especially in India, of the use of recycled plastics in one form or fashion in asphalt concrete at various times. Okay, so these plastics are being used. It's being extensively evaluated, and I'll talk about the types of plastics that are used. Many of you are probably much more intimately familiar with the procedures of plastics, but I'll dive into that just a little bit for those of you who may not be as familiar with recycling of plastics and the nature and properties of those. So when we think about plastics, we have to think about what kind of plastic it is, because as you all know, plastic is not in and of itself a material. It's a class of materials made up of varying polymers of varying length and complexity. That's usually indicated by the small little recycling symbol that you might see on your plastic water bottles or otherwise, that gives us an idea of what kind of plastic that this is. And I've put in this slide a couple of information that I think are going to be useful for us. So in the slide, we have the number. So normally in a plastic, you would see a small number on the inside of this triangular arrow. If that number is 1, then we have PET. If it's a number 2, you have high density polyethylene, and so on and so forth. Now, each of those materials have different applications, but they also have different melting points. Now, I've highlighted 2 of the rows in this table because 2 of these are of actual importance to us in asphalt concrete. The first is high density polyethylene. High density polyethylene is the kind of material that we use in pipes that you might come across in playground equipment and things like that. You might also find high density polyethylene in very, very stiff plastic bags, or even some bottles that we might encounter. Soft bottles. The other kind of plastic that's relevant are the low density polyethylene. Now, the low density polyethylene are the very thin plastic bags that we might use for wraps around food. We might use low density polyethylene bags for shopping purposes or other kinds of things. And what you'll notice about the high density polyethylene and the low density polyethylene is that these tend to melt at about 130 degrees Celsius, or in the case of low density polyethylene, somewhere between 110 and 120 degrees Celsius. The other plastics will tend to melt at much higher temperatures. The ones that are relevant for asphalt concrete tend to melt at higher temperatures. One that's really not very prevalent is polyvinyl chloride, or PVC, largely because of the toxic fumes that come off when you try to heat up PVC at high temperatures, which makes PVC a very non-attractive material for asphalt pavements. Now, to put some context to why at least in the US, recycling plastics has become such a hot topic in recent years has to do with the current recycling rates of high density polyethylene and low density polyethylene. We often hear about, at least before I got interested, a little bit interested in this topic, I would tend to think that a lot of our plastics are actually recycled, but that is far from the case. In the US, at least, the recycling rate for high density polyethylene is around 27%. So of all the high density polyethylene we produce here or use here, we only recycle less than a third of that material. In the case of low density polyethylene, it's significantly lower. Here, low density polyethylene is recycled at a rate of about 6%. And the reason for that difference has to do with a lot of factors, some technical. For example, one of the ways that we recycle these plastics is that we chop them up into very fine pieces and then heat them to a temperature to liquefy and then depolymerize, and we work from there. But for low density polyethylene, because the material, you can imagine a very thin plastic bag, it's very stretchy. And so because of that, sometimes it's not easy to chop those bags up and incorporate back into asphalt concrete. Or not in asphalt concrete, but back into the recycling process. So this low density polyethylene is a material that's actually used a lot, but is recycled very little. We only recycle about 6% of the low density polyethylene that we use. Now, these are the two major types of plastic that we generally talk about when we talk about asphalt modification. But as I'll show you on the next slide, there are examples of using PET, examples of using polystyrene and polypropylene. The difference, of course, becomes when do those materials melt and what is the sensitivity of those materials when they're used. Now, with plastics and recycling plastics, there are two basic processes that are used, the so-called wet process and the dry process. In the US, we're most interested in using the wet process. The wet process is essentially a case where we're incorporating the plastic directly as asphalt binder modifiers. So think of this akin to using SBS modified asphalts, where those plastics are directly incorporated into the asphalt binder. That's typically done at a dosage rate of about 2 to 8%, and we'll generally use low density and variants of low density polyethylene. So we're generally going to be using, for wet process analysis, polyethylene materials. In the dry process, we actually will use the plastic as aggregate replacements. Now, in the case of these plastics are going to be very high melting temperature, very stiff, well cross-linked polymers like polypropylene, polystyrene, and the PET that I described earlier. These materials have to stand up to temperature production issues but can be used in applications. Again, not very common in modern usage in the US. I believe this is a pretty common way of using plastics in some Indian applications, however. There's also a set of processes where we use them as mix modifiers. In this case, we basically introduce them into the mixing drum, even though we realize that those materials may melt through the process. So we'll blow in the high density or low density polyethylene, and then we'll just let it melt into the mix and use it as a normal mixture modifier. And in these cases, the dosage rate is quite a bit lower, but it's also done by the weight of the aggregate. So we're using 0.2 to 1% by weight of aggregate, whereas the wet process, we're using it by weight of binder. So it's a little bit of an apple and an orange kind of comparison. So we do have different methods. Again, the US, most of the interest in using recycled plastics in recent years has focused very heavily on using the wet process. There are applications of using the dry process, treating them as mixture modifiers, where we can add it directly into the mixing drum as a filler-based aggregate or admixture. I'll point you to one excellent resource for more information if you're interested. And this is an article or a book that's freely available online, produced by the National Asphalt Pavement Association. Some of you may be familiar with this, but this was a bit of work produced by NAPA and the National Center of Asphalt Technology. They lay out a lot of the issues and limitations with using recycled plastics, including the issues that I list on the left side of the screen. So one of the challenges with using recycled plastics is that there is not an entire system built around specifying and sourcing the recycled plastics. Right now, it's very much being used in a research case. So you might see examples of DOTs using them, but they're using very special provisional specifications. We don't have standards to describe the specific gravity measurements of recycled plastics. There are not established standards in the AASHTO or in our transportation agencies to deal with melting temperatures and differentiating between alternative plastic sources and their differences in melting potential. We also don't have established methods in the transportation community to deal with ash content of post-industrial recycled plastic versus post-consumer recycled plastic. So there's a lot of unknowns in dealing with sourcing of these materials. It's easy for us to say we're going to use a load of recycled low-density polyethylene, but there's a lot of engineering differences between the materials that might collectively be classified as low-density polyethylene. On the binder characterization side, one issue that turns up a lot is the potential for phase separation. So we may mix the plastic into the binder, but the plastic and the asphalt are inherently incompatible most of the time, and so they will quickly phase separate. This is generally handled during production by constantly agitating the plastic modified asphalt binder. We also have to be concerned about whether these materials are compatible with other additives that we have. A big unknown, and where a lot of interest has been in the last few years, is in this laboratory mixture characterization. What are the impacts? We know that there are potential for reduced environmental impacts from using recycled plastics, but there may be negative impacts in terms of cracking and rutting. And so we need to understand what those exist. And we also don't have a clear idea of what kinds of air pollution impacts we have. And not only that, but a lot of these plastics are contaminated with so-called forever chemicals or PFAS chemicals. And we need to understand how those contaminations might impact the long-term efficacy of using these recycled. So the short story is that there's a lot that we know about plastics, what can be done, what can't be done, but there's still a lot more that has to be evaluated and structured and developed before, at least in the US, those can be used on a widespread basis. Despite those limitations, plastics are becoming an increasingly important topical area for recycled materials. Another material that we often use, this comes in and out of fashion every 10 years or so in the US, but is using rubberized asphalt binder and terminal blended asphalt rubber. We use these to eliminate tire waste. Generally, the beauty of using crumb rubber or rubberized asphalt is that it not only uses a waste stream, but unlike some potential for recycled materials, using this waste product actually improves the asphalt concrete itself. So it's a double benefit. You reduce environmental impacts, but you also create a longer lasting asphalt material. So crumb rubber, we use about 15,000 tons, that's US tons, in the US. In the case of rubberized asphalt, those dosage levels are usually around 20 to 25%, coupled with a gap-graded asphalt gradation. The state of California has been championing the use of terminal blended asphalt rubber in dense graded mixes at dosage levels in the order of 5 to 8%. They are not necessarily getting the benefit from the performance of the rubber at those low dosages, but they definitely get the environmental savings of finding a positive reuse for the rubber materials. Again, not in much favor as it was 20 years ago, but there are also examples of using rubberized friction course. These are usually open graded friction courses that help to cut down on pavement noise. In the city of Phoenix, where I used to live, the freeways in that city were all covered. This was probably 15 years ago or more, with a surface of about 25 millimeters of rubberized friction course. And this cut down on the noise considerably. If you've ever been to the city of Phoenix, you know that the homes are usually built right up against the freeway. Those were topped with Portland cement concrete, and then this rubberized surface course was placed on top and cut down on the noise significantly. So much so that the citizens actually voted to increase their taxes to pay for more widespread usage of these materials. These are the main recycled materials that we find in the US: wrap, RAS, rubber, and in a growing way, plastics. But there are lots of other materials that we use as well. One of them of note is called glass fault. Glass fault essentially includes processed glass as an aggregate replacement. This is used extensively at a time in the city of Baltimore, in the Northeast, more in the Northeast and Mid-Atlantic part of the US. It's not widespread, mainly because the economics don't often work out. In order to make glass fault economically viable, you have to have usually a municipal glass processing plant and a municipal asphalt plant, because there, as a city, you're diverting the waste stream directly to another source of material that you as the city are buying. But not many states find this as an economically advantageous use of glass. One of the minor issues that we worry about on glass fault is skid resistance, because the glass particles themselves have a very low microtexture. That's usually controlled by keeping the volume at a fairly low value. You'll also see glass fault used in non-roadway applications like sidewalks, parking lots, some residential streets, etc. There are also examples of using coal and non-coal combustion byproducts like fly ash. We know fly ash is used extensively in Portland cement in order to lower the environmental footprint of that material. But there are also examples of using fly ash in asphalt concrete. In the US, this amounts to about 11,000 tons in 2019. The material is just metered in as a normal material would be, but it's not very widespread. Only a few states are doing it, but there are examples where this is a viable waste stream. One product that is used, again, very, very regionally, is ferrous slag, which is a byproduct of steel production. Generally, this is only going to be used in states that are producing steel. But we use, in the US, we've used somewhere around 1.3 million tons of steel slag and blast furnace slag in 2019. There are also some examples of using foundry sand, another byproduct of steel or iron production, in asphalt concrete as well. The experience with these byproducts is limited, but there are examples. One of the obvious problems with using ferrous slag is the porosity of the aggregates, and you can see that in this picture here, where these obviously look very, very porous. And so generally speaking, they're used at a fairly low dosage rate so as not to increase significantly the cost of the material due to binder absorption. All right, I'm going to shift gears a little bit now to talk about performance. So I've given you background on what materials are often used in asphalt concrete pavements, and I want to talk a little bit about an important component, which is the performance of these materials. The wrap, I'm going to talk specifically about wrap, but this applies to all recycled materials. We can see a major net benefit of using recycled materials. There's an economic savings, there's an environmental savings, But what's really important to think about is whether or not the long-term performance benefits are there. Because even though it may cost less and it may have fewer impacts, if you're having to replace the material more often, then the actual benefit is lost. And so you don't have that in the long term. Now, if you look in the literature, you can find literally thousands of papers on whether or not reclaimed materials perform better or worse. And the net outcome of all of those studies is it depends. Some studies find that reclaimed asphalt pavements materials perform adequately or equal to non-RAP materials. Some show that they perform worse. The general consensus in this is that RAP-based materials perform better when it comes to rutting and permanent deformation, but not always. There are plenty of studies that tell us something different. The consensus is also that RAP-based materials have the potential to increase the brittleness of our materials and therefore negatively affect the cracking performance. I want to talk about one small study that we did some years ago now for the state of North Carolina to investigate this. So what we did in our study was we obtained typical mixtures from the state of North Carolina. We obtained surface, base, and intermediate mixes. And then we obtained for those mixes so-called RAP equivalents. Now, the RAP equivalent mixtures are produced using the same basic component materials, but using a mix design that incorporated RAP aggregates or RAP material into that mixture. Now, in our study, we used a fairly low RAP content, about 15%. Remember, this was done several years ago when that was a typical dosage rate in the state of North Carolina. That dosage rate has now increased to closer to, as you saw in the previous slide, about 24% on average. But we were looking at a fairly modest RAP dosage rate of 15%. Now, if we wanted to look at the performance of the RAP mixtures, we had to do a series of laboratory experiments. So what we did were AASHTO TP 132, which is dynamic modulus testing. We did axial fatigue testing and permanent deformation tests. We basically wanted to figure out how stiff the materials were, how likely they were to experience fatigue cracking, and then how likely they were to rut and permanently deform. I'm not going to get into the details of how those tests are conducted. I hope you're somewhat familiar with, if not the tests themselves, at least the idea that we need to understand the modulus of the material, the fatigue resistance, and the permanent deformation resistance. So let's look at the dynamic modulus. So again, I hope you're familiar with dynamic modulus. If you're not, then think of this as the overall stiffness of the material, with a higher modulus equating to a higher stiffness material. And then we express it as a function of so-called reduced frequency. And you can think of this as temperature or frequency. So in this domain, we have the behavior at, say, minus 10 degrees Celsius, typical frequencies. And over here on this extreme, we have the values at like 54 degrees Celsius. And here in the middle, it's about 21 degrees Celsius. So in these ranges, we plot the data in terms of what we call S9.5B. These are the non-RAP materials, and then RS9.5B, which are the RAP-based materials. And what you notice when you look at the graph is that the RAP-based materials, apologize, my PowerPoint seems to have frozen. Okay, there we go. Yeah, when you look at these graphs, you'll notice that the RAP materials shown here in the unfilled symbols compared to their equivalent filled symbols are higher in modulus. So what this shows us is that when you add RAP materials to the asphalt mixture, the stiffness increases. This is not necessarily a bad thing. And in fact, for rutting resistance, this might be a very good thing because it tells us that our pavement would be less likely to deform under a prescribed load. When we look at fatigue, I apologize. My PowerPoint seems to have frozen. Just give me one moment, and we'll see if we can bring this back. Apologize for that. So we saw that the stiffness was higher on the wrap mixtures. Now, when we look at fatigue, here we're looking at a typical fatigue S versus N plot. And basically what this tells us is at a given strain level, how many cycles to failure do we have? And if the curve is positioned more to the left, that means worse fatigue performance. The further to the right our figure is, the better the fatigue performance is. So what do we clearly see when we look at fatigue is that at a given strain level, the non-wrap materials are actually performing quite a bit better. Now, what this tells us is the material has stiffened when we added wrap, but it also became more brittle. Now, if we take this material out into the field, and I'll show you some simulations in a moment, we might expect that the field performance is going to be degraded because that wrap-based material is more likely to crack under in-service repeated loading. And that pattern emerged for each of the different mixes. So we see a surface mix, it was affected, the intermediate mix, and then the base mix, we saw a very big impact from these differences in fatigue performance. When we look at permanent deformation, the behaviors look the opposite. Here again, the wrap-based materials are the unfilled symbols, the non-wrap materials are the filled symbols, and you can see that under the prescribed loading, we accumulated less permanent strain with our wrap-based materials than we did with our non-wrap materials. The exact differences vary whether we're dealing with a surface mix, an intermediate mix, or a base mix. So let's step back for a moment. The experiments show us that for these particular materials, when we add wrap, the material gets stiffer, more resistant to permanent deformation and possibly rutting. But the counter is that they're possibly more likely to crack when they're used in service. Now, because we tested these particular properties of our asphalt mixture, we were able to take these and use them in a pavement performance simulation. For us, we used the AASHTO Pavement ME software. At the time we did this, it was known as the MEPDG, to predict the long-term performance of our pavements made with those materials. Now, in that case, here we're comparing the no wrap versus the wrap, and you can see that the no wrap pavement has more rutting, almost half an inch, versus the wrap-based mixture experiences a lot less rutting. This basically confirms the idea that adding the wrap would likely improve the rutting performance of our mixture, which is a good thing. In the case of fatigue, however, we see a different behavior. So in this case, we have cracking reaching about 25% in the no wrap case at the end of a 20-year period. But the wrap case, we actually reached that same cracking threshold in about half the time. So in this case, using the wrap-based material has a negative consequence of increasing the cracking propensity of the material. Now the question becomes, is that still a net negative or not? Is it okay that we have less performance because of all the savings we get up front in terms of cost and in terms of environmental footprint? Well, fortunately, we can take a look at that. We can actually observe and figure out whether or not we have whether or not we're likely to observe a net benefit or a net detriment. We did that using a established life cycle cost analysis with real cost software. If you're not familiar with this, this is produced by Federal Highway Administration. It's considered to be a vetted and approved method of estimating life cycle costs. We also looked at the environmental assessment using, again, a tool produced by the National Asphalt Pavement Association to estimate what are the emissions from using these different materials. And then we asked ourselves a couple of questions. First, we asked ourselves, well, what would happen if we use the no wrap mixture and the rehabilitation schedule consistent with no wrap mixture performance. Basically, what does the no wrap baseline look like? Because this is our target. We want to make sure that whatever we're doing with recycling materials, it's at least no worse than our regular wrap mixture or our regular non-wrap mixture. We wanted to look at the hypothetical case that we use wrap, but it performs equally as well as the non-wrap. Then we wanted to look at what happens with the wrap, given the wrap inferior performance that we would achieve. And then what would happen if we use the wrap mixture, but we acknowledge that the performance is lower and we adjust those conditions. Now, I know this is in this presentation, I'm going through this a little bit quickly, but basically what you can take away is we saw differences in performance, and then we wanted to evaluate the life cycle cost impacts of those differences in performance. So we designed, on the basis of the performance prediction, different rehabilitation strategies that this diagram is summarizing. Okay, the details aren't super important, except that because the wrap material performs worse, we need to do a more frequent maintenance or rehabilitation interventions, which is why in case 3, which accounts for the reduced performance of the wrap, we see a more frequent rehabilitation and repair schedule implemented versus the other cases where we didn't do that and we just observe the performance differences. Now, I'm sidestepping the details of that to get to the main conclusion, which is that when we look at the costs of using wrap, actually looking at these particular mixes, and I think the important part of this is that these are specific to the mixtures we evaluated, the actual net cost of using recycled materials, because they're performing worse, was actually quite a bit higher than what we saw from the control mix. Now, the importance of this in a broader sense is to think about what is the life cycle impact of my design decisions today. And while we may think we can achieve a lower cost because the performance is not the same, we actually can see a much higher cost by adopting what seems to be a sustainable alternative and material. It basically tells us for the need of designing these materials very carefully so that we do get better performance and not just use them blindly as a substitution in the mixture. This is the cost, the agency cost and user cost, again, higher in both cases. Users experience more cost because there are more interventions, and so there's more delay in their schedule. We also see the impact in terms of environmental CO2 equivalents. So this is our baseline. This is what we will get by using non-wrap case, no wrap mixtures. If the wrap performs really well, we get some benefit, but because the wrap doesn't perform as well, we get a net cost. Again, the takeaway from this is that if the wrap materials don't perform as well as the non-wrap equivalents, there can be a negative consequence in terms of long-term costs and long-term environmental impacts. Now, I don't want you to come away from my presentation thinking that wrap is always bad, because that is not the message I want you to have. The message I'd like for you to have is we need to think and we need to be very careful with blindly adopting wrap materials. Here's an example of a counterpoint to my case. This is a study done by Tom Bennett in Rutgers University. Here, again, we have the same basic idea. This time the graph is reversed. So we have strain and number of cycles to failure. So the higher position is better. And if you look at the 0% wrap case, it's actually the worst performing one in these cases. And in their mix, the way they designed the mix happened to result in the higher wrap cases on the mean, on the best fit of this function being better. There is, of course, a lot of scatter, and so there's a lot of uncertainty. But unlike the North Carolina study, this study showed that wrap could be designed with better performance than at least equivalent performance to a non-wrap case. Why does that happen? It happens for a lot of reasons, and I'll highlight some of those. Well, the first is that wrap in and of itself is not a consistent material. I'm showing you an example from a Virginia project. Credit to Dr. Johnny Abush at VTRC for compiling this. These are 3 different examples of wrap materials that would be used or could be used for asphalt concrete mixtures. You'll notice that they vary in terms of color, in terms of gradation. If we broke these apart, there would be different kinds of agglomerations inside. We also have different asphalt contents of these wrap materials, and those wrap materials have different binder grades. So we see, even within one state, we can see variations in aggregate properties and asphalt binder properties. That will lead to inconsistencies in terms of how the materials are used and how they perform in the field. Here's another example from the state of Arizona. Again, 5 samples taken from the same wrap stockpile. And here you can see the continuous PG grade varies from as low as 112 up to 130. This is actually extreme. Now, Arizona is much more arid. It is much hotter. Usually in the city of Phoenix, if any of you have been, you know this, but the city gets into the 40s, 40 degrees Celsius or 45 degrees Celsius in the summer. So it's very, very hot, very warm, and that causes the wrap to be different. But if you look at this wrap from a different state, it also looks different from what we saw in Arizona, or excuse me, in Virginia. Another reason that you see differences in wrap properties has to do with how those wrap stockpiles are managed. This is an issue that cannot be understated, that practices with respect to managing wrap and RAS have to be done very, very carefully. If not, you can get very inconsistent and poor performing wrap materials. So there's a reference I show here from Napa again on how to manage wrap and RAS stockpiles. It's a very, very important document. I'm not going to go through all of the issues, but I am going to show you some examples of the things that can occur on real job sites. But this document goes through how important it is to manage the reclamation process, to manage the inventory, to think about how the wrap is processed. There are lots of different ways of doing that, and how we manage RAS and other things. So this is a really, really important document that if you are interested in looking at RAS and wrap management, and if you're not doing it already, to consult and reference. This is great for a document that's prepared by a group to help understand what's going on, but it's also important to understand what can exist on a normal real world job sites. So all of these photographs come from the state of North Carolina. This is a state that has a pretty robust set of stockpile management practices in place and best practices and guidelines for contractors, but you're going to see differences. So here is one contractor who they have a wrap stockpile. This wrap stockpile is very dark brown, but not black in color. And they're actually stockpiling some sand and fine particles at the toe of this stockpile. So when they take from this, they actually pick up wrap, but they pick up some extra sand as well. You can also see on the image on the right, again, we have this large stockpile that we're dumping on. Here we have both millings and we've got these broken slabs of asphalt that get incorporated. And all of those differences are going to get processed into the final wrap stockpile that's used. Not ideal practices. Here we have a contractor that does a very good job, right? They've got the stockpiles aren't too high. They've got an excavator that's turning over the stockpiles pretty regularly. The stockpile is dark black, which means it's got a consistent asphalt binder to it. And in fact, this happens to be a very fine stockpile. And you can see, again, how they're managing this to prevent segregation and do kind of follow through on the best practices for the city, for the state. Another example, again, we see segregation at the toe. You can see how these stockpiles, keep in mind that wrap stockpiles contain asphalt binders, so they can consolidate. It is possible to walk across these stockpiles. They're very rigid. You'll see that in the next slide. And again, we've got aggregate kind of segregated and stuck at the toe of this, which if they're incorporated, give us inconsistencies in how that wrap material will perform. Here's a case where I don't know if you can see it or not, but this wrap stockpile is so segregated or so tight, it's so stiff that the excavator that takes the wrap out is actually scratching the surface. So the excavator is trying to get the material, but it's so compacted it can't do it. This is a bad management because that material is going to be inconsistent. When it's scratching it, it's going to be changing the properties and so forth. And finally, there are issues related to RAS. So we've got RAS that has to be segregated, and we've got, look at all the nails and bits and pieces that are part of that RAS stockpile and are basically now incorporated into this process stockpile of RAS. Also notice that this isn't covered, so water can get into that and strongly affect the capabilities of that RAS to be successfully used in asphalt mixture. All right. One of the things that kind of highlights all of the issues that we see associated with wrap RAS issues has to do with what I call the wrap RAS binder contribution triad, which basically says that we need to think about how much binder is available from those wrap materials, how much is active, actually available to blend, and then how well that blends together. Now, one of my colleagues, Dr. Castorena, has been doing extensive work to understand this triad over the last 5 or 6 years. I'll highlight some of the main findings so that you can see why it's so important that extreme care be taken with these recycled materials. I'll talk about availability first. So here, when we think about wrap, we often think of it as aggregate that is black in color and that the binder is available to blend. But in fact, within wrap, there are these agglomerations. Now, these agglomerations actually are very stiff. It's almost impossible to break them apart with your fingers. And because of that, those agglomerations hold all of the binder inside and make it unavailable to mix with the asphalt concrete mixture. And that's demonstrated in the schematic here. So we've got the surface asphalt that's available, but then we've got this internal section which is completely unavailable and not mixing with the asphalt concrete. Dr. Castorena and her student Sonia Pape have been championing a novel method where they actually use microscopy to look at how much of binder is available. They can see, as you see in this picture, agglomerations of recycled material that are not becoming undone when it mixes, and they can actually see that through the microscope using X-ray techniques to measure the quantity of material in those samples. I'm not getting into the specific details, but what they have concluded is that the availability for wrap varies quite a bit from one stockpile to the other. Up to 80% in some cases. Those are cases where it's really available, doing a lot of good in the mix, all the way down to 50%. And when it comes to RAS, they may actually get no benefit from the RAS at all. It might not be giving you any binder. None of the binders available in the mix. In addition to getting binder available, that binder has to become active. And this is an area that has been studied extensively by groups in Texas, as well as at University of Parma in Italy. And here they've been looking and trying to figure out, just because the binder is available doesn't mean it actually activates. You might not get enough heat transfer to make the binder blend in the mixture. And in their case, they've developed a method to use indirect tension testing to try and understand how much binder will become available. And they've been able to show that binder availability increases with temperature. So practical application, if the material is processed at a higher temperature, you're more likely to get activity, and therefore that's going to improve the availability and the activity of the binder in the mixture, and you're going to get better blending. And if you get better blending, then you get better performance at the end of the day. So when we have limited activity, the mixture may perform in an inferior way. This becomes increasingly important when we start thinking about cracking, because when we develop the mixtures, we assume that the binder that's there is all acting. It's active, it's available, and it's contributing positively to the performance of the mixture. But in fact, the recent literature on this tells us that not all of that binder is active. And so we actually have a much lower effective binder content in our mixtures. And heretofore, we haven't been characterizing this, which is one reason that you can see some mixes doing a very, very good job and other mixes doing a very poor job, because they're giving you different availability, different activity, and so on. Now, one strategy that has been becoming increasingly popular in the US is to use recycling agents. Now, recycling agents are an old material. They've been used in the US for many, many years, sometimes sold under different names, but they're basically, the basic purpose of a recycling agent is to try and rejuvenate the mixtures and make the binders look like they originally did when they went into the mixture. So we're trying to reclaim or rejuvenate those asphalt binders. Sometimes these materials act more like softening agents, which is not what we want. Sometimes they act like extender oils, again, not what we want. And so in the last, I would say, 5 to 8 years, there's been a considerable amount of work done, first at Texas A&M, ongoing work at University of Nebraska, at NC State and Virginia, to understand and classify different recycling oils. There are a lot of different products out there, and specifications are being built and developed all the time. This is a quickly evolving area, at least in the US, to try and increase that activity and availability of the asphalt binder. We've looked at this a little bit in terms of recycling agent study with Virginia. Here we're joining together rheological evaluations and chemical evaluations, and doing a lot of different study with recycling agents of various types and grades and different wrap materials. One of the things we're learning is that these recycled materials have very different impacts to rheology of the binder. So I show you this example where we have a different recycling agent. This is just a snapshot of some of the results. You can see that this bar here corresponds to the binder and the wrap itself. And as we add the recycling agents, they become softer. At high temperatures, they become softer. But if you look at the low temperature case, especially when we oxidize and age those materials, you can see that each recycling agent basically gives you the same rheological behavior. So these recycling agents, the thing to think about is, how are they affecting the initial rheology of the system, but then how are they propagating and affecting the rheology in the long term? Because some of them may look really good early, but may not look very good later on in the life. And of course, we are interested in long life pavements and making sure that those work very well. Now, the last thing I want to mention here today is, what is the impact if we do not get good contribution from the mixture? Now, this is work, again, that Dr. Castorena has been looking at quite a bit. And what she's been able to devise is a methodology to design the mixture so that we better leverage known contribution levels. She has developed a technique where she can create or identify the availability of the asphalt binder and adjust the gradation in a way that gives us a similar voids and mineral aggregate. And as a result, we can actually see improved performance by carefully engineering the asphalt mixture, taking into account that not all binder contributes to performance. Again, the basis of this is, we need to think very, very carefully when we deal with these recycled materials about how they interact with our virgin materials and yield good or, in a negative case, bad performance. So what she's done is taken a couple of three mixes. Each of those mixes, she's created two different variants, a so-called control mix, which is basically standard practice on mix design. What you'll notice is because not all of the binder is active, we actually have a fairly low recycled binder content. She redesigned that mixture by taking into account how much binder was actually contributing. This was not simply changing the binder content, although one could do that, but in fact adjusting the gradation to match and yield an acceptable volumetric combination and concentration. And then what she found was actually, as judged by the CT index, she could actually increase the amount of wrap material in the mix and at the same time improve the performance of that mixture. So the offshoot of this is that it is possible, there is evidence of using recycled materials, designing them very carefully to ensure that their performance is not negatively affected. But what can't be done is to blindly add in recycled materials and hope that they perform better. Because as we showed in the North Carolina case, when you do that, you run the risk of truly negatively impacting performance. And if that happens, then all of the benefit that you see in using recycling materials may be lost because of increased maintenance costs, increased disruptions to traffic because those repairs are being made, and other negative consequences. So what I want you to take away from this is we just need to be very careful using recycled materials, not to run into using them for the goodness of their resource consciousness and now end up losing performance and creating actually a worse situation that has more negative impact on the environment and on our economic well-being. I believe these slides are posted, so I put a few additional resources for those that are very interested in this recycling issue. As I noted, there have been many projects on these issues, especially around wrap in the US in the last, I would say, decade. And these are just pointing you to a number of those in addition to what I talked about with the NAPA resources for your interest. I'll wrap up with the last couple of statements. In the US, and I'm speaking to you from the US's perspective, we produce a lot of asphalt mixture on a daily basis. We should, as good stewards of the taxpayers' money, and I think of stewards of good environmental consciousness as civil engineers, do our best to improve that production in ways that make positive reuse of waste streams. But we cannot and should not allow our roads to become linear landfills where we're dumping any and all waste streams into those pavements as a way to get rid of them. What we've seen from the science and the literature is that it is possible to positively reuse those materials in ways that are mutually beneficial, not only to society at large, but to the asphalt paving industry as a way to cut costs and actually extend what can be done within the costs that are and the funds that are available with respect to providing smooth, safe, reliable roadways. But it is paramount that we consider how our decisions affect the long-term performance. That is super critical. Without that thought in our minds all the time, we simply are going to be running the risk of having more negative consequences than positive benefits. And that is not what we as civil engineers, or at least I as a civil engineer, feel is an appropriate use of our expertise and our experiences. With that, I want to thank you very much for your attention. I apologize. I know this was a lengthy in English presentation, so I appreciate your attention, and I look forward to answering any questions that arise. Thank you.
Thank you very much, Professor. We have two questions in the chat. The first question is, Would it work with rubble rush, or would it work as rubble rush or fly rush, referring to RAP and RAS, I guess?
So I don't know the context of that question with respect to RAP and RAS. One of the things that, when I hear rubble, I think about some of the plastic modifications and using um, some of the more cross-linked polymers and plastics. I think that's a possibility to use those materials in the same way, basically as an aggregate replacement. I'm not familiar with people using rubble ash as an aggregate replacement. One of the challenges is, how do you control those materials reliably? We can certainly add waste materials into asphalt concrete, but we need clear specifications and standards to deal with them. In the case of fly ash, as a direct replacement or a direct addition to the asphalt mixture, there are examples of using those. So specifications and standards exist, and those certainly can be directly used. And that's in asphalt. We can use them in Portland cement concrete as well.
Okay, pretty good. We have a second question. It's a little bit weird. La pregunta creo que en español es qué experiencias y diferencias particulares deberían tomarse en cuenta para pavimentos reciclados constituidos con betún asfáltico y versus asfalto modificado con polímeros, ¿verdad? La pregunta de Yerko. Disculpa, ¿es sí o no? Porque en inglés sería which experiences and differences should be taken into account for recycled pavements made of asphaltic betún asfáltico versus polymer modified asphalt.
Yeah, I think I can kind of understand the basics. If I restate it, I think the question is, when you use normal asphalt binder, that's what I was talking about, versus polymer modified binder, what are the particular issues to consider? I'll speak from the US perspective on that. I hope Yurko, this is a good enough answer for your question, but generally speaking, when agencies use polymer modified binder, they use considerably less or even no recycled asphalt mixtures. Many times they view using polymer as a luxury, as a high value pavement, and they don't want to take the risk of adding recycled materials on top of that. Now, in North Carolina, we still allow recycled materials in polymer modified mixes, but the amount is much lower. We're limited to only 18%. Now, another piece that's unknown at this point is whether there's a benefit in the recycling process later on. So 10 years from now, when we recycle the PBM mixture, will there be a benefit to the long-term performance? And that's really an unknown issue. Some agencies, because of that, actually make sure that they capture all of the PMB mixtures that are recycled and use those in very high value assets as well. I don't know if that answers the questions, but yeah.
Más o menos, la respuesta es que no se usa, no hay datos a largo plazo sobre los usos, pero normalmente no se usa materiales reciclados con asfalto modificado con polímeros porque no quieren correr el riesgo. Sin embargo, es lo poquito que pude obtener. Tengo una pregunta para usted, doctor. I have a question for you, sorry. The COVID-19 pandemic affected several sectors of the society. So was there any impact on the use of recycled materials on pavement in these 2 years?
That's a good question. I have not seen, and none of our research has suggested that the amount of recycled materials has increased or changed. It is possible, but I don't know. I don't think that that's saw an increase because of COVID-19. One of the let me back that up. So I think one of the impacts of COVID-19 and other associated geopolitical forces have been in the US. It is harder, as I understand it, to find SBS modified asphalt. And because of that disruption, I think it has prompted many researchers and even some suppliers to accelerate their interest in using recycled plastics as a replacement for SBS modification. I don't know that they have been successful, but I know that has accelerated it. And maybe COVID-19, I don't know if it's more of the geopolitical disruptions or the COVID-19, or they're kind of working together to cause that. Now, another thing in the US for during COVID-19, a lot of the construction projects kept going. So we had a lot of construction going on that was not disrupted. So, the construction industry kept working. And so the amount of recycled material would have been similar with or without the pandemic.
Okay, pretty good. Thank you, Professor. We have another question on the chat. The first question is, given the high PG at high temperature obtained from recycled asphalt pavements associated with the phenomenon of aging and oxidation, what rejuvenating agents and in what average dose, saving the particularity of each wrap, gave them better performance?
Yeah, very good question. So there are probably about a dozen different individual products that exist on the market today for recycling agents. I'm going to go back to this slide to kind of give you some sense of that. There are about 4 different methods that have been developed to classify them. I'll let you kind of read on your own the reports that exist, but I'm going to highlight them on the slide. This ASTM 4552 NCAP method, probably the most widespread method is the NCAP method. Nebraska, University of Nebraska, and then Texas A&M. And these classification methods have basically focus on what the chemistry or the rheology properties are of the recycling agents. So there are different ways of categorizing them. Generally speaking, we categorize them as either petroleum-based, organic or non-petroleum-based, and emulsion-based. And there are other classifications as well. Now, dosage-wise, it very much depends on the specific recycling agent, on the target of the rejuvenation, and on the wrap stockpiles you have. So if you want a rule of thumb, a good rule of thumb is somewhere between, I would say, 1% and 5% recycling agent dosage, based on the studies we've been involved in. There are probably cases that are below that limit and some that are above that limit. What most agencies seem to be doing is adding the recycling agents in a way to rejuvenate the high temperature grade, so that they get as much rejuvenating agent in that mixture as possible and still have a material that's unlikely to rut. So usually you're going to add as much recycling agent as you can so as not to decrease the high temperature grade below 64. And that's as high as you go. And that changes all of the rheology. But yeah, the focus has been on durability and cracking. And so we're trying to put it, most people are trying to put as much in there as possible to avoid that cracking problem.
Okay, the final question is, for wrap, do they generally use foamed asphalt?
Yeah, not really anymore. The prevailing approach, and I'm sure there are examples, in North Carolina we don't. The prevailing approach in centralized plant recycling is, if you're going to use anything, you might use an emulsified or an additive in the binder, like a recycling agent, to try and mobilize that. Several years ago, I would say now probably 8 years ago, there was a big push to use warm mix asphalt. I think that probably still exists some, but it's not the same that it was, 5 or 6 years ago. A lot of people are adding in warm mix additives directly into the binder and circumventing that need for foaming altogether. Again, there are probably examples of people doing it in various places, but I don't have the sense that it's as widespread as it used to be.
Okay, finally, we have a greeting for, one second. We have a greeting for Gabriel Maceda de Brazil. He's studying his PhD on North Carolina State University. So
Okay,
that's,
yeah, I know Gabriel.
the final, that's the final reading. Thank you so much, Professor, for this exposition. We expect you to come back for another exposition in another symposium for several years in the future. Thank you, and please say goodbye to all the attendees. And well, yeah, that's it.
Okay, thank you very much. I'm honored to be here. Thank you for the invitation, and I enjoyed speaking. And I am impressed with this group meeting late in the evening during the week. That's impressive. I think that speaks to the passion for this field, and I'm very happy to be here. Muchas gracias.